Hello, everyone. My name is Matthew Reinhard. I'm a PhD student at the University of Florida, working with Dr. Zachary Slepian. Today, I'm going to be talking about computing the trispectrum for Axion inflation. Now, this talk is going to involve a lot of theory, but I've included an image here of the dark energy spectroscopic instrument, or DESI's focal plane, embedded on the night sky, because ultimately nature will tell us what is true about the universe. And so we want to test the predictions of Axion inflation by using the data made available from large galaxy redshift surveys such as DESI. Now, we know that the laws of physics are invariant under certain symmetry transformations. And some of these include time translations, spatial translations, and rotations. Now, these are three examples of continuous symmetry transformations. An example of a discrete symmetry transformation would be a parity transformation. And in fact, all known fundamental forces are invariant under a parity transformation, with the exception of the weak force. Now, the concept of parity is fairly important throughout the rest of this work, so let's start by defining what a parity transformation is. So a parity transformation is an inversion of all spatial coordinates. If we consider a position vector on the bottom left here, if we apply a parity transformation, all of these coordinates pick up a minus sign. Now, an example of a parity transformation that we're all familiar with from our everyday lives is looking at ourselves in the mirror. So here we have a right-handed coordinate system, and the mirror image over here has the z-axis inverted. So this is a parity transformation with an additional 180-degree rotation. And the mirror image is actually a left-handed coordinate system. So this is why when you look at your right hand in the mirror, it appears as a left hand. So we know that on large scales, our universe is highly homogeneous and isotropic. But what about handedness? So we can actually define the handedness of a group of 4 galaxies in the following way. Let's consider sitting on one galaxy. We'll call that our primary, and that'll be represented by this red dot over here. And we're going to draw vectors to 3 other galaxies, with R1 being the vector to the closest of the other 3, R2 being the vector to the next closest, and R3 to the furthest galaxy. And if we trace around this tetrahedron that we've formed here, moving from R1 to R2 to R3, we see that we move in a clockwise fashion. Whereas if we look at the mirror image of this tetrahedron on the right, and we again trace around from R1 to R2 to R3, we actually move in a counterclockwise fashion. So a tetrahedron is actually the simplest shape which cannot be rotated into its mirror image. It has a well-defined parity. So a natural question one might ask is, are there an equal number of left or right-handed galaxy configurations? Or is there an imbalance? In a paper published in 2022 by House, Slepian, and Kahn, they actually attempted to answer this exact question. They made a measurement of the 4-point correlation function using the BOSS galaxy survey data, which is the simplest statistic sensitive to parity violation. So the 4-point correlation function is defined on the bottom left here as the correlation of the overdensity delta at 4 different spatial locations. And they actually detected parity odd modes in the 4-point correlation function with a detection significance of 7.1 sigma, indicating that the large-scale structure of our universe is not invariant under a parity transformation. And Philcox 2022 also found evidence of parity violation from the 4-point correlation function at a lower statistical significance. So if in fact the large-scale structure is not invariant under a parity transformation, this begs the question, what could have caused this parity violation in the large-scale structure? We know that all fundamental interactions are parity symmetric, except for the weak interaction, but the weak interaction is very weak and didn't really play a role in the formation and evolution of the large-scale structure of matter. Therefore, any parity violation in the large-scale structure must have come from some new, as yet undiscovered physics early in the universe. If there were a parity violating interaction during inflation, this could potentially seed the parity violation that we observe at late times today. So one particle that could be responsible for the parity violation in the large-scale structure might be the axion. The axion is a hypothetical particle that was conjectured to exist as a solution to the strong CP problem of quantum chromodynamics, or QCD. The QCD Lagrangian contains a CP violating term, where C here stands for charge conjugation and P for parity transformation. Charge conjugation takes particles to antiparticles and vice versa. So this term on the right here is the CP violating term in the QCD Lagrangian, where theta is a parameter that can range from 0 to 2 pi, but is undetermined by the theory. Experimental measurements of the electric dipole moment of the neutron have found that theta must actually be very small, less than 10 to the minus 9. So the strong CP problem is the question, why is theta so small, possibly even 0? Perhaps the most popular solution to this problem was introduced by Pesce and Quinn, and their solution involved the introduction of a new global U1 symmetry. And the breaking of this symmetry leads to the production of a new particle called the axion. The vacuum expectation value of the axion exactly cancels the CP violating term in the QCD Lagrangian, therefore solving the strong CP problem. Now, the standard model of inflation actually preserves parity, so it could not explain any parity violation observed in the large-scale structure. Axions, however, are pseudoscalars, meaning they pick up a minus sign under a parity transformation. So we consider here an inflationary model with an axion coupled to a U1 gauge field. So the model is given by the action right here, where phi is the axion field, which actually plays the role of the inflaton driving the expansion of spacetime. F mu nu is the field strength tensor. This is constructed in terms of A mu, which is not necessarily the electromagnetic force potential, but some general gauge field. And I want us to focus on this last term in the action here, which represents an interaction between the axion and the gauge field. And this term actually picks up a minus sign under a parity transformation because the axion is a pseudoscalar. So this parity violating interaction could potentially source any parity violation that we observe in the large scale structure today. Now we work in the Coulomb gauge, so the time component of the gauge field is 0, and the spatial components can be written as a Fourier expansion, where epsilon are the circular polarization vectors, little a are the annihilation operators of the gauge quanta, capital A are what we'll call the mode functions, and lambda is being summed over plus or minus 1 to represent the two different circular polarization states. but the equations of motion of the gauge field show that we actually get large growth in the A plus mode functions, and the A minus mode functions are actually quite negligible. So for the rest of this work, we consider only the A plus mode functions given by this expression right here. Now the density curvature perturbations, zeta, are given by minus h, the Hubble parameter, times delta phi, which are perturbations in the Axion field about its background value, and phi dot here is the time derivative of the Axion field. So we can write these Axion field perturbations as a Fourier expansion in terms of these Q mode functions. And these mode functions can be separated into the component due to vacuum fluctuations, as well as a component due to inverse decay of gauge quanta into axions. So we can actually write our trispectrum as two different 4-point functions, one due to the contribution of vacuum fluctuations, and the other due to the contribution of this inverse decay mechanism. And since this inverse decay is sourced by this interaction between the gauge quanta and the axions, this is what's going to be producing a parity-violating signal, this second term here. So this is what we'll be focusing on. Now this Q inverse mode function can be written as the integral of a Green's function against this source function j. Now j is defined here in terms of the creation and annihilation operators and the mode functions a plus of the gauge field. So if we insert this expression for the Q inverse modes into the curvature trispectrum, what we get is this expression on the bottom here, specifically for the parity-violating part of the curvature perturbation trispectrum. And it's written in terms of the 4-point function now of these source terms. So this 4-point function is going to involve all possible contractions of the different creation and annihilation operators of the gauge field. And there's a nice diagrammatic way that we can count up how many contractions we're actually dealing with. So each of these 4 vertices represent an interaction between the gauge field and the inflaton field, where the red squiggly lines correspond to the gauge field and the black line the inflaton. So if we consider the internal line of momentum Q1, there are 6 possible contractions that we can make. And once we make a choice for Q1, there are now 4 possible contractions for the Q1 minus K1. We don't want to contract with Q3 here because that would give us a disconnected diagram. We were considering the one loop contribution to the trispectrum. So once we make a choice for our second internal line, the Q2 minus K2 has 2 choices. So we actually have a total of 6 times 4 times 2. That gives 48 different possible contractions. So we will need to integrate over these 48 different terms in order to compute the trispectrum. So here I have one single contraction, and this will be very similar to all the other ones, except for a rearrangement of the momenta in the delta functions, and possibly an interchange of some of these complex conjugates on the different gauge field mode functions. So this is a very high dimensional integral. If we were to integrate out all delta functions, we would still be left with a 12-dimensional integral. So instead of integrating out the delta functions, what we do instead is we expand the delta functions. We make use of the delta function expansions listed here and insert them into our contraction to yield this expression. Although we picked up some extra integrals over these dummy variables x1 through x4, we've also separated out the 4 momentum integrals into 4 integrals of the exact same form. So if we can do one of these integrals, and we can do all of them. So I have at the top here an integral of this form, and the dot product of these polarization vectors can be given in terms of these the angles of the momentum vector q and the momentum vector k minus q. And if we insert this dot product expression into the above integral that we call the I, we end up with 7 different terms. But each of these different terms is actually a convolution. So we can make use of the convolution theorem to turn this into a problem of taking a sequence of Fourier transforms. And what's convenient about the convolution theorem is it gets rid of that shift by the vector k. Notice each of these inverse Fourier transforms of these functions f and g only depend on q and not k minus q. So we are actually able to analytically compute all of the angular integrals associated with these Fourier transforms, and we got it down to just this single integral over this dummy variable u shown at the top here. So we've been able to greatly reduce the dimensionality of integration of the trispectrum, making numerical calculation of the trispectrum much less computationally intensive. So in conclusion, we've shown how to simplify the calculation of the trispectrum for Axion gauge field inflation. We're going to use these techniques to numerically compute the trispectrum for a large range of external momenta combinations, and then we're going to use the DESI data to make a robust measurement of the galaxy port PCF and search for signatures of this Axion gauge field inflationary model, allowing us to constrain the physics of the early universe. Thank you very much for listening to my talk.